Hello everyone. We're going to continue with section 7.6 on molecular structure and polarity. The learning objectives in this video will be explain the concepts of polar covalent bonds and molecular polarity. And just a note there, we've already talked about polar covalent bonds in a previous video, so we'll not get into the details of what that is, but in how that concept connects to the concept of molecular polarity. And then the second learning objective, assess the polarity of a molecule based on its bonding and structure. Okay, so let's talk about molecular polarity and dipole moments. So we talked about this idea of molecular polarity in an earlier video, and that we could talk about the bond as having a polarity to it in some cases, and we could represent this with a vector. So we're showing the polarity of particular bonds in these two examples, where the vector is the arrow is pointing towards the part of the molecule, or I shouldn't say part of the molecule, the arrow is pointing to the atom in the bond that has a greater tendency to have the electrons that are shared in that bond. So when we talk about the bond polarity, we're looking at just between the two atoms involved in a bond. So the vector is a way of illustrating that. We can talk about this as being something called a bond dipole moment. So it is a distance over which we have this difference in charge based on the sharing of electrons. There's an equation here for that. We're not really going to be applying that equation. We can also have polarity within the molecule as a whole, in addition to the polarity we have between individual bonds within the molecule. If the molecule is polar, we can talk about the dipole moment as being for the entire molecule. What we want to talk about now is how to make that determination of whether or not the molecule is polar. And this will be done more qualitatively as opposed to using that equation that we saw. Although that is possible to do it in that way, we're not going to do it in that way for this class. So let's look at some examples. When a molecule contains polar bonds, those polar bonds could interact in a way that either create a polar molecule or a non-polar molecule. If there are not polar bonds, then the molecule will not be polar. So here we're showing an example of carbon dioxide. So in carbon dioxide, we have a total of two bonds, a bond from carbon to oxygen, which is polar, and another bond from carbon to the other oxygen, which is also polar. We're showing here the carbon dioxide molecule as the shape that it has, which is linear. So with this linear shape, the way this works out is we have this tendency to pull electrons toward one oxygen and a tendency toward pull molecules towards the other oxygen. Those two tendencies will actually cancel out because they are going in opposite directions. So overall, there is zero dipole moment for a carbon dioxide molecule. So we would say that it is nonpolar because of that. Even though it does have two polar bonds, those polar bonds will cancel each other out, leaving us with a nonpolar molecule. In contrast, we see this molecule of H2O. It also has polar bonds, so the bond from hydrogen to oxygen is polar, and we have two of those. However, in this case, we don't have a linear shape. We have a bent shape for this molecule. And because of the bent shape, the way this works out is that those two vectors do not cancel, and we have an overall vector for the whole molecule. So overall, we do have a dipole moment, and we have a molecule which is polar. In order to determine whether or not a molecule is polar, we have to consider the shape of the molecule as well as whether or not each of the bonds are polar. So these are some of the classic examples of this. We will be doing a lot more examples of making this kind of determination in the lab. So there are more examples here to look at. So just kind of a summary of this. If a molecule is polar, it has to have at least one polar bond within it, a polar covalent bond, and then have a structure so that the sum of the vectors of the polar bonds do not cancel out. And again, we'll get some examples of this in the lab. There are many interesting properties of polar molecules. This is something we'll actually talk about in more detail in a later module. But you can see some of them here in terms of how they may align with an electrical field.